moving into the scientific principles, we're finding paradoxes and holding on to them. So where do we go from here? I'm going to talk about an experiment which verified this nonsensical way of behavior in the universe. It's called Bell's experiment. Because Einstein was convinced that particles carried secret information, hidden information in them, which could explain some of the things that we were seeing in quantum physics. So that if you really could understand deeply some of the properties of certain particles, that it would make sense what the experiments were showing us. And so last week we had, or no, this week, we're introducing two characters. They might be back next week. So this is Alice and this is Bob. I'm not sure who started this, but there was particle A and particle B, and somehow it became Alice and Bob. So this is my Alice, and this is Bob Ross. Love Bob Ross. So he's my Bob. And we have a source of entangled particles. Entangled particles means that somehow a pair of particles were created that are related to each other. In this case, we have Tweedledee and Tweedledum. Tweedledee, if Tweedledee is up, Tweedledum is down. If Tweedledee is right, Tweedledum is left. So they're opposite particles. There's qualities of particles called spin, polarization, things like that. For now, we're just doing Tweedledee and Tweedledum are an entangled pair. When the source creates this entangled pair, one moves towards Alice and one moves towards Bob. One of them will be in one orientation and the other will be in the opposite. And we don't know what their position is until we detect them because they're particles. So when these particles, Tweedledee and Tweedledum particles, are released, they can be up or down, they can be left or right, they can be any direction. But what we know is that whatever direction this one is, the other will be the opposite. And so if we have a detector at Alice, a little bit closer to the source than Bob, if Alice aligns her detector up and down, and so does Bob, say Alice detects Tweedledee up, Bob will detect Tweedledee down. And if we do this many, many times, we'll see the same results. Alice detects Tweedledee up, Tweedledum down. The problem is, if you start to look a little more deeply, something strange is happening. So as soon as you know that Tweedledee is up, you know that Tweedledum is down. So one particle is up, the other particle is down. Doesn't matter how far away you are. Could be at the other side of the universe. And immediately, once you know the position of this particle, you know the position of that particle. So you have information traveling faster than the speed of light. This violates this causality that was so important in general relativity. But it gets even more tricky. We're just going to keep adding to this experiment because you got to do it slowly. So if Alice changes the orientation of her detector, so instead of up and down, it's now to the right. We still don't know which position this particle is. It can be in any direction for 360 degrees. If her detector is to the right, Tweedledee will be either right or left. Not up and down, either right or left. And Tweedledum, if Bob's detector is the same, will be the opposite. So Alice's detector, which way it is facing, will determine the orientation of the particle. So her choosing the detector's orientation determines how the particle will be measured. So I'll say that again. Her choice of position determines how this particle will be measured. It's the same kind of particle. Previously it was up or down, but because her detector is no longer up or down, the orientation of the particle has changed. So Alice's choice is affecting the position of the particle. The orientation of the particle affects this over here at Bob's detector. And in fact, however Alice orients her detector, and however Bob chooses to orient his detector, they find that whatever particle Alice has, Bob will have the inverse of it all the time. And if there was secret information communicated between these particles, we would see a distribution of positions different than what the experiment shows us. So the experiments show us that statistically, over many measurements, it's exactly the opposite. We have Alice and Bob always reading the opposite position of particles. And the particles will change their orientation depending on how Alice and on Bob orient their detectors. So what is it about choosing the position of a detector that changes a quantum state just by interacting with it? So we're actually determining quantum states just by choosing the detector. So this is something that Einstein called spooky action at a distance, because the particles communicate faster than the speed of light. Instantaneously, we know what the orientation of particle B is. And this is really the foundation of quantum computing, and also in encryption studies, encryption sciences as well, is this fact. So the positions of Alice's particle will look like a random distribution. And Bob's will also look like a random distribution until Bob knows how Alice chose her detector, and then he can see that the random distribution that he sees is actually just the inverse of Alice's. And so what we've been able to do is go billions of light years across the universe and run this same experiment. So this was just released in August, this study. So now Bob is a quasar a few billion light years away, and Alice is another quasar a few billion light years away. And what they did is they took the light from the quasar, a photon from the quasar, and they chose the orientation of the slit based on the color of light coming from the quasar. So a quasar is altering the light that's coming out. So essentially it was a random way to determine what the slit orientation would be. And likewise, Bob over here, the position of his detector was also determined by the color of the light coming from the quasar. So several billion light years across the universe, a source of entangled particles is released here, first to Bob and then to Alice. And we find the same results, that the quantum state of the particle here is the opposite of the quantum state of the particle there. And it wasn't a selection effect sort of from the people making choices about the detectors, no communication. The only communication was a photon from this quasar, a few billion years old, and from this quasar, a few billion years old, determining the quantum state of something here on Earth. So they completely randomize it and find the same results. So as soon as one particle interacts, its pair has the information immediately. I don't know why, just full disclosure. There's a lot of theories of why or how. Quantum physics is not really good at explaining why or how, but it can use the results of the experiment to do things like develop quantum computing or doing grading encryption technology using this information.